I have one final topic to discuss while we are still talking about a single explanatory variable related to a single response variable, and that is consideration when studying bivariate relationships. Many of these considerations will actually carry over to when we have more than one explanatory variable, but they're easier to describe when I just have one response and one explanatory variable. So let's talk about them now. Relationships found within one range of the data may change outside of that range. I can demonstrate this for you. Suppose we have some x variable, some y variable, and let's take a look at the relationship of y and x across this whole range on the axis. Okay, so if you looked at that, you would say, hey, there's a pretty strong relationship here. We have a linear regression. These points seem to fall pretty nicely around this line. Here we have residuals can be shown here. All looks well. Pretty nice, strong relationship. But imagine, let's see if I can get rid of a few of these things I drew here, including that line. Imagine if we had only looked at the relationship in a restricted range, say from here to here. Let's take out this one. In that range, if I had looked at that, this is what I would have had. That doesn't look to be near as strong a relationship. If this x-axis had only been along here, and if I didn't have these points up here, you would have looked at that and said, well, I'm not sure, is there a relationship or isn't there? Maybe a little bit of a relationship. So we just went from a strong relationship to a, at best, moderate and probably weak relationship only because we looked at a limited range of the data. So that's what I mean when I say that relationships found within one range of the data may change outside of that range. The next thing to keep in mind is that association does not imply causation. Just because two variables are associated doesn't mean one implies the other. Now, certainly what we want, what is fundamental to science, is to say that the variation in y is being caused by variation in x. And we have to think about how to design studies to be able to ascertain cause. But if all we're doing is collecting data and looking at relationships among variables for data that we collected without doing anything else other than observing, not creating some sort of experimental design, then we don't necessarily have causation. We don't know if we do or not. And that's because two variables may be related because a lurking variable influences both variables. So, going back to my little pictures here, if I have a variable here y that I think I'd like to be able to say that x, variation in x is causing variation in y, well, so just because I have an association between them, and I'm going to go ahead and indicate an association rather than a causation with that curved line. Just because I have an association, that may be because over here there's some other variable, let's call it z, that is influencing both X and Y. So Z is influencing X, Z is influencing Y. So anytime Z changes, what happens? X changes and Y changes. So it makes it appear that X is influencing Y when in fact Z might be influencing both of them. So two variables could be related because there's a third lurking variable that influences both. The next idea here is the strength of a relationship based on one unit of analysis may appear weaker or stronger for a different unit of analysis. So let's look at that. So let's suppose that we're looking at the relationship of, let's see. Student parental income. So we have parental income here, and we want to know if that seems to be related to the achievement of the students. And so let's suppose that we were looking at that relationship and using each individual student, we're looking at their parental income. We're finding out that data, which of course would require the consent of the parents. And we find that, yes, indeed, there is this relationship that we see of income to achievement. Higher income seems to be related to higher achievement. And the way I have it drawn here, it's a moderately strong relationship. But now let's suppose we change the unit of analysis, and let's suppose that, let me go ahead and erase this. So let's suppose that we have students from a class that's located in a low-income, low SES area, and there are the students here. And then let's suppose that we had students that were in a little bit higher income area here. And let's suppose that we have students that are from even a higher income level, and some of those might be down here as well as up here. And let's go even higher. Okay, so I tried to draw the picture so that it was similar to what we had before in terms of that relationship. But imagine if we changed the unit of analysis so that what we gather data on is each class. So perhaps we take the mean of the students in those classes. So we have the mean of the student here in one class, and we have the mean of the students here in another class, and then we have the mean of the students here in a third class. It looks like maybe it's around here, and then we have the mean of the students in a fourth class, looks like around here. Notice what's happened with all this is that we've ended up having an almost perfect model. That is a very strong relationship because we use the classes instead of the individual students. So again, the point is that if you alter the unit of analysis, you should expect your association to change. So association is not free of the unit of analysis. How you choose that unit can depend upon what you find. So if a researcher here had simply looked at classes and taken the individual mean, it would have been a very different picture and a very different research report than if the researcher had looked at individual students. And then finally, outliers can become influential observations and dramatically change our estimates. So once again, a picture, one final picture here. So we have some variable x and y, and let's suppose that we had data that looked like this, and we have this regression line that goes through. And suppose we say, oh, wait a minute, there was one more piece of data and we forgot to record it. Let's go ahead and put it in, and that data point was right there. Okay? We call that an outlier. Why? Because it's very unlike the other points in terms of its pattern, and those can occur. And that one particular outlier down here could in fact change our regression line so it looked more like this. Okay? One outlier can be highly influential. Now, the influence of that outlier depends upon where it occurs. So if I had an outlier here, then this line is actually not going to be affected much. You can think of it kind of like the principles that you see when you are on a teeter-totter. So when you're on a teeter-totter, what happens? If someone is out near the end, they're much more influential than if they get near the fulcrum point, near the center of gravity. And that's the way outliers work. They're more influential when they're out near the ends than when they're in the center. So even though this point that I drew here is still clearly an outlier, it's very different than the others. It doesn't actually have much influence on that particular regression line. So when we say outliers can become influential observations and dramatically change estimates, they can, but they won't always. We would have to look and study that and see where those outliers are. So these are all considerations when studying bivariate relationships. These are going to come into play when we get into more advanced models, but this is the easiest time to sort of consider why these concepts work in a way that makes sense to us.